All right, welcome to phase 4 of the Espresso project, which has to do with type checking. Hopefully this video won't be quite as long as the previous one, but let's see. Let's get cracking on this. So, type checking. I think everybody's probably aware of what the basic idea of type checking is, but let's just take a quick example, and this is from the handout. For the Espresso project. So if I have something that says A equals 89 plus hello, then we could ask, does this make sense with respect to plus and equal and the fact that 89 is an int and hello is a string. So in reality, there's a number of different questions we have to ask here, and that is, does this operator work with an integer and a string? And in most cases, people would probably say, no, it doesn't, because what does it mean to add 89 to a string? Now, it turns out in Java you can actually do this, and Espresso as well, and you get a string with the value 89 HELLO. So if your language allows overloading the plus operator to work as a concatenation operator between anything and a string or two strings, then you could say that this is either an error if you don't allow it, or something that is of type string, because a string plus any other thing just becomes a string. Now, then we could ask ourselves, is this assignment legal? And the answer to that is, of course, that it depends on A's type. If it's a string, then yes. Otherwise, not. All right, let's try another one, which is probably a little more obvious. If I say int a equals 89 plus 1.2. We could try to do an analysis that, and we can try to make it look like somewhat formal, and we can pretend that we have a function called type, and we can ask, what's the type of a? Well, obviously the type of a here is an int, because we've defined it to be an integer, so we'll say that it's an int. All right, then we can ask, what's the type of 89? Well, that's probably also an int. What's the type of 1.2? Well, it's the double. As an aside, if I wanted it to be a float, I have to put an f after the 2 in 1.2. Similarly, if I wanted the 89 to be a long, I would have to put an L after the 9 in 89. So numbers that can be int default to int, and numbers that can't, that are decimal numbers, default to double. Right, now if I have an int and I add a double, then by coercion, which is basically an automatic cast that can be done, and may be done so by the compiler if there's no lack of or loss of precision. So we can turn the integer in this int plus double, this guy here, into a double, And then we have double plus double, which gives us a double. So therefore, the type of 89 plus 1.2 is a double. Now, can I assign a double to an int without loss of position? And the answer is no. So, not legal. Okay. Before we jump into it, let me just say a few overall things. So basically things to keep in mind. And the first one is to study the type-related parse tree nodes. If we go and look in the AST directory, and we search for things that extend type, then we get well, actually, we get a class hierarchy that looks like this. We have type at the top, so that's a generic superclass for all possible types. Then we have a primitive type, which represents all the primitives, so things like int, float, string, bool, char, long, double, etc. Then we have a class type. And don't confuse a class type with a class decal. Anything that's defined, so any variable or parameter or field that's defined to be of a class will be of class type. We have an array type if you do arrays, and we have a null type. And I think the null type is probably only used for void, if I'm not mistaken. Yeah, that's one. That one is. It's not going to be in the parse tree. It's going to be used for type checking purposes only. Right. So if we look at this guy here, it has many useful methods. Maybe we can just take a quick look. I already prepared the handout here so we can actually go and look at it. So let's look at a type first. We can see here the type is an abstract class, so that means that it doesn't exist as an actual type in the parse tree or in the type checker. It's just a nice way to have something be a superclass. And if we look down, we'll see that if you are a type, you have to implement signature and type name. We can ask for a type prefix. This is a little more useful when we get to code generation, so we can skip that for now. We can ask here if two types are identical. So if something is a type, you can call identical on it, and you can pass it another type. We can figure out if it's assignable, i.e. if it's something we can assign to. And then we have a function here which is immensely important, and this has to do with assignment compatibility. And basically, this it's a static function, so it takes in two types. So it's not something you call on a particular type, but it takes in a type of a variable and a type of a value, and then determines if those two can be used in an assignment with the variable on the left and the value on the right. And if we look at it at the implementation, we can see that if the variable is identical to the value, then sure, we're good. If both are numerical, then we turn them into primitive types, and then we check to see that they are related in such a manner that the type of the variable, which is the one that's going to be on the left in an assignment, is quote unquote greater than the value. And greater here, of course, means that you can make the assignment of the values or of the type val to the variable of type var without loss of precision. Otherwise, if we have class types, we check to see that one is a superclass of the other, and so on and so forth. We can ask if something is an integer, array, boolean, byte, short, char, long, class, void, null, string, float, double, numeric, integral. And remember, an integral type is anything that's a whole number type. So it's an integer, short, byte, character, or long. A primitive type, we can parse the signature. I can't remember what we need that for. We'll come back to that. This is all code generation related stuff with width. Is super? Well, it takes in two classes and it tells you whether one is a superclass of the other. And that's about what we have in this class. But do take a look at it. It is useful. Let's take a look at the primitive type as well. Now that we're here, and we can see here that the types of the primitives are closely related to the kinds in the literal file. So let's see. We can construct it. It's not abstract. We can call this static function called ceiling on two primitive types, and then it gives you the higher of the two. I'll come back to that in just a second. We'll do an example, and we can see here that if I call ceiling, then I get an integer back, which is just the kind. But I could also call ceiling type and get an actual type back. You can turn it into a string. You can get the name of it. This is code generator related stuff, I think. You can get the kind. You can get the signature, and here the indentation leaves a lot to be desired. And then that's about what we have there. So let's just talk about primitive types for a second here. So we need to discuss and understand what a type hierarchy is. If I were to pick an integer, so let's say we have an integer type here, then I could ask the question, which of the other primitive types can hold an integer value if they were declared as variables? And if we think about this for a little while, we'll get to the conclusion that longs, floats, and doubles can hold integer values. So you can sort of say that above here are long, float, and double. What's below? Well, so in other words, which values can an integer variable hold? Well, that's something like char, byte, and short. Now, if we keep sort of expanding on this by saying, okay, if I take a float, then which values can a float hold and which types can hold float values, then we should be able to build a tree-like structure. Let's see. So in Java and Espresso, and Espresso is just like Java, just for ease of use when you want to try to cross-compile something. We have a hierarchy that looks something like this, and I'll draw it first, and then we can discuss in a second why this might not be the best thing to have. But I have an int, which of course can be held. Oops. By a long. Now, this one here you might bark at, because this says that a float can hold a long value, but a float is a 32-bit and a long is a 64-bit. So how is this even possible without loss of precision? It isn't, and it's probably bad, but that's how Java does it, so we'll do it as well. So we get a double there. Down this way we get char short byte. And then somewhere all by itself, we get a string and a Boolean. And the height of these is of really no importance. We can put them anywhere we want. What matters is that they're not connected to the other guys. So we have a hierarchy of primitive types that looks something like this. Now, what we could try to do, just sketch over here on the left, maybe a better hierarchy. Now, people are probably going to be annoyed if they can't take an integer value and put into a float, or a long to put into a double. So we're going to have to sort of connect that in some way. But we could do something like this, and then we could arm wrestle about this char business as well. So an int can definitely go into a float, and it can go into a long. If an int can go into a float, then a long can go into a double. And then we get something like this. Now, if you wanted to implement your own language and you said, well, these are the rules that I want for my primitives, that's perfectly fine as well. And they make perfect sense. Right, so that was the type and the primitive type. Shall we take a look at what's in class type? Well, as you can see, not much. There's a constructor and a MyDeco. You can get the name, you can turn it into a string, you can get the type name and the signature. Okay, easy enough. What's the other one we needed? Array type. All right. So let's see. Constructor, we can figure out what the base type it is, what the depth is. We can turn it into a string and get its signature and its type name. And that's basically it. So this is what we have to work with in order to do type checking. So before we go and look at the handout, the handout code, we need to talk a little bit about what it is that we have to try to do. So the tasks associated with type checking. Well, ultimately, we want to fill in a bunch of visit methods from the visitor, but This time I'll actually go through every single one of them and tell you what they are, and they're in the handout as well. They're just empty, so you got to fill them in. So could we maybe here say ultimately fill in visit methods. And one thing that's important here, up until now, all our visit methods have returned null because we haven't had a reasonable value or need for a value of any kind. What we need now is we need all nodes that have a type must return it. Oh, and before they do that, they must also set their type field. I don't know if you've noticed, but if you go and look in expression, you'll see up here at the very top that we have a type field. This field must be set by the type checker. So any expression, of course, has a type, and a visit to that expression will return that type, but will also set the type field. Right. Now, there are a few things that we have to do in order to be able to compute this type. So ultimately, if something, and this is typically expressions, so if something has a type, compute it. And we've seen with the example here on the first page that this is a binary expression. It has a type, and we need to compute it, and there are some rules for how we do that. So for example, here we went and figured out what the type of this was. We figured out what the type of that was. Then we figured out whether both of those types are compatible with the plus operator, and then we figured out that the overall type was just the ceiling of these two. So in this case, we did something where we said, grab the type of this guy, and it turns out that that will just be a visit call, because a visit call to anything that has a type will return that thing's type. A visit call to this, so we would get a primitive type of type integer back here, a primitive type of type double back here. Then for plus, we would have a rule that says if both sides are numeric, then we're good. And then we would say the overall type of this thing here is, well, an int and a double, so that's the ceiling. I'll take the ceiling type of those two. That gives me a double type, so the overall type of this binary expression will be double. We'll set the type field of that expression and return it. So if something has a type, compute it. And set the type field. If something uses other values, and need specific types, then check them. So an example of that, of course, is if we have an if statement. So we can actually just do an example of that. If something 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 else something something something. So if I look at this, then of course this is going to be an if statement. And it has no type because it's a statement. But this must be a Boolean type. So actually, let's call that E1, let's call that S1, and let's call that S2. E1 must be a Boolean. S1 and S2 must be checked. So if I do a little example and I write down things I need to do, then implementing it is fairly straightforward, because if I have something like this, then I can get the type. So if the if statement is is, so is is the if stat node, then is dot, oh, I think it's called expr, isn't it? Should we just check? It is called expr. This returns a type. And we can ask if that's a Boolean by saying is Boolean type. Actually, so let's just go back into our type file here. And is Boolean type, there we go. So oops, right here. Okay. So we can just say is Boolean type. And for this stuff here, well, that's easy as well, because it's just is dot then part dot visit and is dot else part dot visit if it's not null, because that could be null, right? So we in many cases don't have these super calls or visit children calls as we've had in other phases. We pick the parse tree apart, and then we visit the parts individually. In particular, if we visit things that extend expression or something that has a type, then we capture that type in a variable, probably because we want to do things with it. So we sort of need to visit that explicitly as a one thing, like we can see here. So we might capture this in a type, in a local variable, and then call the is Boolean type on that, and then produce an error message if it's not. And if it is, then visit the then part and the else part if it's not null. And of course, this is This is a statement. This if guy here, so it doesn't have a type. There's no dot type field to set. So in that situation, it's perfectly fine to return a null. Now, 4.2 has to do with finding the right method to call when you have an invocation. Originally, I meant for everybody to implement that method, but it is very, very, very long and very, very tedious. So I've actually left the implementation in the handout, but I do want to just say a few things about how we can do this. So this has to do with section 4.2 in the handout. Now, if we didn't have method overloading, that would be easy then, because then there would only be one candidate. The problem here is when we have method overloading, there could be a number of candidates. So I think I want to illustrate this with a simple example. So let's do example 1 here. If I have one implementation of f, and I say f of 7, f of 1.2, f of 3 as a byte. Then I can ask, which of these are legal? Well, 7 is, this 7 is an int, isn't it? So let's see, this is an int, this is a double, and this is a byte. And I can ask the question, can I take something of type int and fit into something of type int? Yes, of course I can, so that's perfectly acceptable. So we'll say that's good. And it calls that one. Well, there's only one to call, so we don't get much of a choice. Can I take a double and put into an int? No, I cannot. So this one here is illegal. Can I take a byte and put into an int? Yes, I can, and I get this one called. Okay, so that might not have been particularly enlightening, so let's try another example. And that's the situation where I have, let's say, up here, maybe I should have put a body in. Oops. And then again, I could say f of 7, f of 1.2, f of byte 3. Now let's try this again. This is still an int. This is still a double. And this is still a byte. Now it turns out here that we have a f that takes in an int, so we have a match here. So we have a match between the actual type and the formal type. And it turns out for the next guy, I also have a match. But now what about this last one here? Can I take a value of type byte and put into a parameter or variable of type int? Yes. Can I take a byte value and put into a double variable? To which the answer again is yes, I can. So which one should I pick? Should I pick this one or should I pick this one? So we could, for this guy here, say, since int is below double in the hierarchy and byte is below int, then byte is closer to int than to double. So what we do in this situation, we find the least specific. sorry, the least general, or if you wish, the most specific. So this one here will be a call to that one. So we get that, but not a match. Okay, let's try another one. Let's give it a few more parameters. So if I do something like this, and I have a number of calls, if I say f of 3.4 and 1, f of 1 and 4.2, f of 3.3 and 4.4, and f of 7 and 3. Then if I quickly go through and type check these, and of course the way I can do that in the implementation of the Espresso compiler is just visit the parameters, because then since they extend expression, they will have a type field that gets filled in and we will know what their types are. So this comes back as a double and an int. Shall I just do them all here? Int, double, 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 int, and int. So if we look at that first one here, what we will do in order to do this in sort of a methodical way is to sort of look at all the candidates, which are all of these, and throw away all the ones that definitely don't work. So if I look at this guy, double int, oh, there's an actual match. So it doesn't get any better than that. But if I wanted to do sort of an elimination round, then the next time I would say, oh, int and double. Well, I can't put a double into an int, so this one here would go, leaving just this one here, which is the one we would call regardless. So this one here is fine, and it calls this one. Now it turns out to be the same thing with this guy, just the other way around. We get this one. This guy here now has a double and a double, but this first double can go into a double there, but then we run into a problem with this guy. This second double can go into this one, but we run into a problem with that one. So neither of these are candidates, which means that we've now eliminated all the candidates that we had, which means that we have nothing left. So this one here is none, no candidates at all. Okay, that's not so good. Now what about this last guy here? Well, let's see. 7 and 3, that's an int. An int can go into a double, and an int can go into an int, so we'll keep that one. An int can go into an int can go into a double. We'll keep that one. So both of these are candidates. So now we have to try to eliminate the most general one, and we can do that by picking pairs of candidates and then comparing them in such a manner where we pretend one is an actual call and the other one is the method being called. So in the situation of these, we would pretend, let's start that this guy here is the formal parameters, and we will pretend that this guy here represents the actual parameters. If I could take values of these types and put into these parameters, these formal parameters, then in some way, since both of these work for this one, but if these values could also go into those, then this one here is more general than this one, which means that we could throw that one away and then try it all over again and keep going until we can't eliminate any more, or until such time that we have just one left. Right, so let's see, can I put an int into a double? Yes. A double into an int? No. So I couldn't eliminate this one here by pretending that these were the actual parameters. Well, let's try to do it the other way around. So now I'll pretend that I have actual parameters of type double and int and formal parameters of int and double, and see if this one here is more general by being able to hold those Well, let's see, we have a problem here right away. Int cannot hold a double, although this int can be held in this double. So this one does not eliminate that one, and this one does not eliminate that one. So now we end up in a situation where I couldn't narrow my list of possible candidates down to just one, because neither of them would eliminate each other. And the only thing we can do in this situation is to say no most specific or least general method could be found. Now, this doesn't have to be just a numbers game. We could take that a little further as well. So let's try to do that. So what was that? 3, 4. So let me give you a class hierarchy, and this is from the book called The Java Programming Languages. The Java Programming Language by Ken Arnold and James Gosling, and you can find this on page 108 to 111. And it looks something like this. I have a superclass called Dessert, under which I have a scone and a buttered scone. And over here I have a cake and a chocolate cake. And then I'm going to have 3 methods, and they look like this. I don't know what morge is, but I have a feeling it's the equivalent of quaffing, just with solids. But if anybody knows, let me know. So this is dessert D and scone S, and cake C, dessert D, and chocolate cake CC, and scone S. So 1, 2, 3. And then I have 4 calls. The first one is the dessert reference, and the second one is a scone ref. Second one is a chocolate cake ref and a dessert ref. Then I have chocolate cake ref and a buttered scone ref. And finally a cake ref and a scone ref. Right, so what are the candidates for this first? Well, let's see. If I have a dessert ref, and a dessert ref can only go into dessert things because there are no superclass, then I cannot take this dessert ref and put into a chocolate cake or a cake. So it can only go into here. So now let's see. Can scone ref go into here? Yes. So the only option I have is number 1. So we pick 1 and be happy with it. So let's see the next one. a chocolate cake ref and a dessert ref. So it's one of these guys and then it's one of these guys. Now, can I take a chocolate cake ref and put into a buttered scone formal parameter? No. To a scone formal parameter? No. To cake and dessert? Yes. So my chocolate cake ref can go into dessert, cake, and chocolate cake. So on this first parameter, all of them seem possible. Second parameter here is a dessert ref. Well, that can't go into a scone. A dessert cannot go into a scone, but a scone can go into a dessert. So this is out. This is out. That leaves me just with this guy. Oh, well, we only have one in this case, so we pick number 2. All right, so now I have a chocolate cake ref. I know that that can go into dessert, cake, and chocolate cake, and I have a buttered scone ref. Well, that can go into scone, dessert, and scone. Okay, so now I have 1, 2, and 3. Now we have to play the elimination game. So let's just put a little purple star here, and what we'll have to do is we'll have to pick these in pairs, and then we'll pretend that one of them is the formals and the actuals. So shall we start with 1 and 2? So in other words, if this is the formals and this represents the actuals, if this guy can hold that reference and this guy can hold this reference, then this is more general and we'll toss it away and keep this one. So can I put a cake into a dessert? Cake to a dessert? Yes. Can I put a dessert into a scone? No. So this gave me nothing. All right, let's turn it around and try 2, 1. Can I put a dessert into a cake? No. Can I put a scone into a dessert? Yes. Well, that didn't give me anything either then. Right, so let's try 1 and 3. So we're asking, can I take a dessert and put into a chocolate cake? No. All right, so we're already in trouble there. No. Oops. Now something needs to start happening, else we're going to get in trouble here, right? So 3 and 1. So formal parameters are represented by 3. So can I take a dessert into a chocolate cake? No. Okay, that's not good. I'm wondering if we're doing this right. So let's try 2 and 3. Okay. Actually, 1 and 3 should have worked. Hold on. We did something. Let me go back and redo some of this stuff real quick. I want to go back to here. So these are my formals and these are my actual parameters. Oh, we did that wrong. So can I take something of chocolate cake and put into dessert? Yes. Can I take something a scone and put into scone? Yes. Ha! Sorry about that. So that works, which means that we've now eliminated 1. So now I have 2 and 3 left. So now we gotta try to do that. So let's see. 2 and 3. So the formals are 2. So that's these guys. Can I take something of this type and put into here? Well, yes, because a chocolate cake can go into a cake and a scone can go into a dessert. So in this case, again, we get that, and then we get rid of this one. So that means down here we get 3. And of course, we could have seen that by just looking at it as well, because chocolate cake and scone is, oh, that was a butter scone reference. but scone is definitely better than dessert here, and chocolate cake is better than dessert there in terms of better meaning, closer in the class hierarchy. Okay. So let's see, what do we have now? We have, what are the candidates? So a cake and a scone. Can a cake and a scone go into that one? Yes. Can a cake and a scone go into that? Yes. Can a cake and a scone go into that one? No, it cannot. So I get candidates 1 and 2. But look, we've already seen here that 1 and 2 cannot eliminate each other. So we're now in a situation where there is no least general. So no method to call. So all this stuff this is implemented by find method. And remember, call visit on the actual parameters before a call to find method. Because find method uses the .type field of the things that are being passed in, and if you haven't visited those parameters, then those type fields will be null. Now, this is sort of as far as we get if you just read the handout, which leaves a fair amount to be desired. Now, before we look at the code and talk about some of the things we have to do, all the type checking. We can say here that type checking is chapter 7. And I think I will do the following and say, do not read chapter 7 yet. And the reason is that chapter 7 is a somewhat theoretical framework that could be implemented for type checking. And it would be really nice to try to do that for the Espresso compiler, but we don't have that right now. So I think you'll be better off reading the handout and watching this video, and then write the implementation of the type checker with those tools, because chapter 7 describes a number of things that aren't implemented in the Espresso type checker. And if you wanted to do that yourself, it would be a tremendous amount of work that you would have to do. So don't read chapter 7 yet. Just pay attention to this stuff and listen, and we'll get through that, I think. Right. So now let me just pull up my type checker here. So I suppose we could try to open it here. And what we can see is here's this find method, and it just goes on and on and on. It's actually nicely commented, so you can read it and understand it fairly easily. But it's a long method. See, we're at we're at 205 lines plus the one that nicely lists the candidates. So that's stuff that you don't have to do. Right, then we have some fields here. We have a class table. That's just all the classes. We have the current class, and then we have something called current context. And maybe I'll just say a word about current context here. And basically, it always points to whichever class body decal we are working on. So whenever we enter, and of course they are static init decal constructor decal method decal, and to a lesser extent field decal. The one where it's important is this one here, because for a return x, we must check that x can fit into the type declared as the return type. The problem, of course, is by the time we hit the return statement, we've long gone past the method declaration. So if I update my current context every time it changes, then I can always just figure out which class body decal I'm in. And when I need to figure out what return type it is, which is when I'm in a method declaration, then I can do so simply by referencing the current context. All right, let's go back to the code and see. I can't remember what this other stuff is. We'll come back to that. There's a constructor. And then now they come down the file, and I've left all the printing in. So visit array access expression. Well, let's just take that one and think about it, because now now what I would do is I would do a piece of paper like this for every single parse tree node that it appears in this type checker. And then I would say, right, let's do an example, and it could be something like a f of 3. And then I would say, all right, let's find out what the accessors are called real quick. So we will go over here, open up array access expression, and see that they're called target and index. Okay. So this is target, and this is index. Now I can say target and index. What has to be true for target? Well, it must be an array. An array type. What about index? It must be integral. It doesn't have to be an integer, it could be a long. Now, it turns out that there are predicates in our type.java that can do that. So basically, for the target, we go and visit it, and we grab its type, and then we check that it's array type, and if it isn't, we throw an error. For the index, we go and visit it, grab its return type, and check that it's an integral type. So what else do we need to do? Well, array access expression, should we just call it AE? AAEs type? Well, it should be the base type of the array, shouldn't it? Or it should be the type of AA with one set of brackets less. So let's just see. Just looking it up here. Yeah, so basically we can say here, if the depth is 1, then it's the base type. And the base type you can get from the array type. Otherwise, it's a new array type with the base type of the target, but depth 1 less. And that's it for this guy. So if I do these things and I write down a page like this, we'll do a couple of more of them. I'm not going to do all of them for you. That would sort of defeat the purpose. But we'll look at a few more. So let's see the next one here. There's no your code here, so that's because what's the type of an array type? Well, it is itself, right? So we just return that as it is. Visit new array. Right. Then we have to see if we can remember what a new array is. So let's do a new page here. So and if we don't remember, then we could open here. Now I know we should probably not look at all these array things because they are more related to Espresso Star. So actually, maybe I will skip this and let the Star people shine themselves. So yeah, let's actually skip that and go to something a little bit less Espresso Star. I've written this guy assignment compatible for arrays because you might need that, and it's a pain to write yourself. We can come back and talk about that. More array stuff. Let's see, assignment. I actually think I've done that one for you. No, I haven't. I've done some of it for you, and let's see what I've done. So let's just look at it at the top. So for an assignment, I go and visit the left-hand side, and I go and visit the right-hand side. I know that the left-hand side is really not something that is of expression type, but it is in the way that we parse things. So it has a type, and we can visit it. And also, the way we are going to implement visit local decal and param decal is just to have them return their types. So we have types on the left and the right. Now, as it says here, note that as.left should be of name expression or field ref class. What else could it be? It's the only thing you can assign to, right? Name expressions representing locals and parameters, and the other one representing fields. Then we just simply ask, hey, is it assignable? If it isn't, then throw an error. And then here's a trick that you need to remember, and that is how to figure out if a name expression is the name of a local, a parameter, or an actual class. If an expression is an instance of a name expression, and that name expression's my decal is an instance of a class decal, then your name expression is actually not to a local or a parameter, but to a class, and you can't assign to that. So mentally make a note of how to check that, because that's going to come up and again and again. And then what I do is I switch on the operators, because there are a number of different assignment operators. Don't worry so much about this this constant stuff here. What's important down here is basically this guy here. And that just says if V-type and E-type are not assignment compatible, then throw an error. And that's basically it, right? If I can't assign something of type E to a variable of type V, then we have a problem. Now you can do the rest for the remaining operators. Should we just make a note of those? See what they are, so we don't miss any of them out. I have that one, which I've already done for you. Then I have this one, that's multiplication, division, modulo, plus, and minus. These all sort of go together because they're numeric guys. Now if I look at these, then what sort of operations am I allowed to do with this? Well, if I have, just maybe make a small little note up here. If I have x op equal y, then that is exactly the same as x equals x op y. So if I'm using multiplication, division, mod, minus, and plus, then bar maybe this plus for strings, then the rest of it would require things to be of numeric type, right? And I would also have to have this guy be a higher type than that guy, so I have to have assignment compatibility between those two, and both of them have to be numeric. So both left and right numeric, and assignment compatibility between left and right. Actually, let's just use x and y up here. So both x and y numeric, assignment compatibility between x and y. So basically x must be able to hold y. And then down here we can just say plus equal may work on strings. Okay, what else do we have? Well, we have these funny guys. Left shift, right shift, actually right shift, and I have this one here as well. Now that doesn't work on strings, that's for sure. It works on integral types only. So we can say x, y must be integral. Okay, what else do we have? We have and equal, or equal, and XOR equal. And the rules here are that they work on integral, so both have to be integral, or Boolean, both. If they work on that, then the overall result is an integral, or is the same left-hand side, yeah. So type of x is the overall type. Same thing with that one. And I think those are all the assignment ones. We could have maybe fitted that on. No, we couldn't fit on that side. Right. The next one we have is, and I want to talk about that one as well. Oh, at the end here, just make a note here that, look, I'm setting the type as.type to be that of v-type. That's the left-hand side type. That makes sense. Print it out and return it. Now, I didn't put in anything in binary expression at all, and this one is big. So let's talk about that one in much the same way that we've done with the other ones. We'll call it BE, and it looks like this: some expression, some operator, some other expression. Now, there's a number of different ways we could attack this, but I think what we should do is we should, in general, just visit the left-hand side and the right-hand sides and get the, I think actually, so this one here is left, this one is right, and I think this one here is up. So let's say that L type is the type of left. So basically we would say be.left dot visit this. And similarly, to get the right type, I think this was a capital T. Oops. Type of right. And if we do that at the very beginning, now we can just switch on the operator's kind. And let's see, we have a number of different ones again that we can group together. We have less than, greater than, less than, equal, and greater than equal. We have equal, equal, and not equal. We have and or. We have and, or, and XOR. We have plus, minus, multiplication, division, and modulo. We have right shift, left shift, and rotational right shift. And then we have one more. Let me just see if I can make a little bit of space here. Which is the one that you always forget is a binary operator, which is instance of. Right, so let's take them in order. So if I have less than, greater than, less than equal, and greater than equal, then there's no doubt about the fact that both of them have to be numeric, right? And the overall type, well, let's say, so see, L type must be numeric. R type must be numeric. BE.type, well, it's a new primitive type. Of Boolean kind, right? Because what is the overall type of an equality? It's a Boolean. It's either true or false. Right. Let's see. What did we have then? We had equal, equal, and not equal. Well, we can't just say that both of the things here have to be numeric, but there are a few things that we have to check here. If L type is equal to R type, so this is basically just identical, then it's perfectly, it's probably perfectly fine. except if either is void. So they can't be void type, but that aside. If that's the case, then b.type is, well, the same as it was up there, a new Boolean thing. If they're not identical, then we could have a left or right that were name expressions, and they cannot be class names. Oh, that's sort of that's another little exception. If either is a name expression, no class names. Now, I'm just thinking here, what happens if I stopped here, then we would be in a situation where, well, if L type and R type are identical, then I can compare integers and integers, or an integer and an integer, but I couldn't compare an integer and a double, and I really kind of want to do that. So if both L type and R type is numerical, then that's okay as well, and be dot type is still the same thing. All right, so that wasn't too bad. What do we have then? Then we have those guys, and they work on booleans only. So L type and R type must be booleans, and if they are, then be.type is a new primitive boolean. Okay, ampersand or and XOR, well, they have to be either both boolean or both integral. So both either bool or integral. If they're both bool, then the type is a new boolean. If they're both integral, now we got to be a little careful. Then the type is the ceiling type of L type and R type. So that's ceiling type. And the ceiling type you can find in the primitive, I think it's in primitive type.java. And we need that because what happens if you're anding together an integer and a long, then you want the overall result to be a long. Right, then we have plus, minus, mod, multiplication, and division. If L type and R type are integral, no, are numeric, then we're fine, right? So L type and R type, both numeric, then be.type is again the ceiling type of L type and R type. But what if they're not both numeric? It could be, well, that's basically the only thing they can be, except for plus. If either is a string, then the overall type is a new primitive string, which leaves just the shift operators, an instance of, yeah, let's do the shift operators, shift, and rotational shift. Then we need integral types for both. So both L type and R type must be integral. And BE.type should be that of L type, because that's the one that we are shifting. As a side of remark, I don't know if there's anything that tests this. Bytes, shorts, and characters get promoted to ints. So if L type is byte char short, then change it to int. And finally, instance of. Well, we have to have some class types here, right? So remember, an instance of looks something like something. Instance of something, and this must be a class name. So why don't we just look that up? Check that right is a name expression with a string that is a class name. And L type must be of class type, and overall BE.type is a new Boolean. And that's it for binary expression. Well, let's see, what else do we have? Cast expression. I'm not going to go through all of these, I think. Cast expression. Well, that has to be a class name. This has to be of class type. Let's call that class D. Then C must either be a subclass of D, or D must be a subclass of C. And you can use the is super method to check that. C invocation is just like an invocation. It's just of a constructor, so that's not too bad. Class decal. Let's see if there's anything important there. Now I do want to go through invocation, so when you have invocation and get that working, you can do C invocation fairly easily. Now in class decal, remember to set the current class, and then I have some code that just checks that I don't repeat any interfaces, but I don't think there's anything that tests that. So here's one that I will do for you. That comment there, system.out, you can throw out. So visit constructor decal. It's a class body decal, so current context should be set to CD, and then just go and visit the children. So super.visit excuse me, CD. Right, so that's all there's to that. Let's see what we have next. Oh, DoStat. Let's talk about that one. It looks like do some statement while some expression. Now, this guy here is probably called, I think we did that in red. This is probably stat, and this is probably expr. Expr must be a Boolean, and stat must be visited. And we need to visit that in order to get it type checked. If you don't visit it, it doesn't get type checked, right? So if there is a statement, then go and visit it. So if you can do DoStat, you can do forStat, and you can do whileStat as well, because they are indeed very, very similar. Field decal, I don't know what all this mess is here, but it looks like I've done it. So just yank that out. Field reference, I've done as well, because it was a bit of a mess. forStat we just talked about. IfStat, well, that's an easy one as well. The expression has to be Boolean. We actually talked about this at the beginning of the presentation here. And then you have to visit the else and the then part, and the else part could be null. Invocation, right? So let's actually talk about invocation, because that one is a little complicated. So let's do that on a clear page here. Now, what does an invocation look like? It looks like some expression, e1 dot some function. Actually, let me just call that e1, e2 dot 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 en. This guy here is the target, and these are the parameters. I think they're called, aren't they? Let's see. Yes, params. Now, in order for this to work, we need to check that that the target is not null. So, well, actually, it could be. So we can say here, if null, then the target class is current class. If not null, then visited must be of class type, and its myDecal is the target class. So by just visiting it, if it has a non-null target, I get something back that is of hopefully target class, hopefully class type, and if it is, then I can grab the target class by looking at the myDecal. Now, if you want to do stuff with strings, then you have to be able to support a dot length and a dot char add, but we can talk about that later. So so far so good. Now if I've managed to make it through this, then I know that my target is the right thing. It's a class. So now we need to deal with the parameters. So now we say visit parameters, and that's actually fairly easy to do, because this is a situation where I can just say in dot. I think the invocation is called in dot params dot visit. I don't care what they are. I just want to make sure that they get visited here, right? So now we can call find method, and it gives you back a method declaration. So you might have to cast that, and remember the target class that we found over here. Now we're going to use that to get all methods. Those were the ones you found in get class hierarchy method lookup from the phase you were working on before. Then the method name. That's just the we can just extract that. That's this guy here. And then we have to give it in dot params, and then we're going to give it a true. This is true because we're looking for methods. Right, so now if I'm going to continue down here. If we get null back, no method found. So that's just too bad. There's not much we can do. We can call that list candidates with the appropriate things, and it'll list out the ones that could be possible candidates. Otherwise, in dot target method equals what we got back, and in dot type is well, it's the return type of whatever we got back. Now, if you can do this invocation, then you can do basically the same for a C invocation, where it's the this or super that determines what your target class is. If it's a this C invocation call, then your target class is current class. Otherwise, it's the super class. And if you can do both of those, you can now also do a new, because the new is an implicit constructor invocation, and the target class is of course always the class that you are creating a new instance of. Right, so that's visit invocation. Literal, well, you just create a primitive type that represents that literal. Method decal, let's see, is there anything? Yeah, remember to set the context. I do that there, so that one line there should just be something that visits the children. Name expression, I'll let you struggle with that one a little bit yourself. New, we already talked about, that's the same as invocation. Return stat, more than you'd expect, right? So that's probably why I did it. Static initializer, I have a feeling that all you got to do here again is set the current context and visit the children. And super, well, you just got to get the superclass of the current class if it has one. If it doesn't have one, we create an error. Switch stat, that's also Espresso Plus, so there's a whole bunch of different fun stuff to do there. Ternary. That's also Espresso Plus, So I'm going to skip that for now. That's already done. Unary post and unary pre. Let's actually talk about both of those. So for the unary post, actually let's do them in order. So for example, it's some, and now I say expression plus plus here, but we know that that expression has to be either a field or a this has to be a field, a local, or a parameter, doesn't it? So we can check we can use instance of. Actually, it could be array access. If it's a field, then it's a field ref. If it's a local or parameter, it's a name expression. And if it's one of these, it's an array access expression. And that's basically it. And the type is basically the type of the expression. Oh, that is not enough. Type of the expression must be numeric. So for plus plus and minus minus, do the same as you did up here, right? For plus or minus, then we just need numeric. And for not, we need Boolean. And for comp, we need integral. And again here, byte, char, short, become integers. Next is the while statement, I think. Okay, there's the var in between. If we have a var, then if there is a initializer on that var, then it has to be assignment compatible with something of the type that is associated with the variable declaration, which is why we have that mydecl in var that comes in handy, so we can get the type of the actual declaration. So there has to be assignment compatibility between the type of the declaration and the type of the initializer, and the type of the initializer, of course, can be obtained by just a simple visit. And we have a while statement, and we already talked about that, which means that we are basically done. Shall I just do the var here? So a var is x equals something in a declaration of the form type x equals something. Shall we call that expr? And the type must be able to hold a value of expressions type. Let's just look at the assignment. So work list says familiarize yourself with the many methods. Yeah, we talked about that. Determine which parse-tree nodes have elements that need to be type checked. Well, we've gone through that as well. Determine for each node what these things are. We determine the parse-tree nodes. We've done that. Read and understand the section about how to determine which method to call. We've done that. Use the build file to test, etc., etc., etc. I think that's it. An hour and 40 minutes, so almost an entire hour shorter than last time. This phase is not super hard. It's a little longer, and it requires a lot more coding. So there's more typing to do. There's just more to produce. But hopefully this introduction makes things a lot easier. Right, so let's stop here, and if need be, we can come back and look at some of the ones we skipped for the Espresso Plus and Espresso Star cases later.